Okay, so now we are going to continue into our lectures covering reaction dynamics. And what we're going to start with is collision theory. And I posted a review video for you on collisions and the mean free path. So if that stuff is a little foggy for you, you might want to review that because we're going to connect now how collisions and mean free path can connect to kinetics. And specifically, what we're interested in is how collision theory manifests in the bimolecular or second order reactions, either A plus A to go to products or A plus B to go to products. Or, of course, we recognize that then dA by dt for reaction 1 might be negative K times A squared. Or for reaction 2, that would be negative K times A times B, where we note the negative sign is just telling us that the rate is negative. Okay? And so what we're interested in doing is seeing how collision theory can give us a first principle expression for the rate constant. And we recognize that the rate constant will be proportional, okay, to what I'll define as sterics, okay, which we could think of as, if you recall, this is sigma, or the collisional cross-section. So that's one proportionality for our K. It's also going to be proportional by some frequency of collision. And that's actually going to be proportional to the square root of T over mu. That's given to us from our Boltzmann distribution of velocities. And then finally, there's going to be some minimum energy requirement that's also given to us by Boltzmann via the molecular partition function. And recall that goes as the exponential of negative EA over RT, where EA represents our activation energy. So we recognize our rate constant is going to be some basic form of sterics or collisions considered by the frequency of those collisions and by some minimum energy requirement for that. Okay? So if you recall, sigma, the collisional cross-section, equals pi times d squared, where d is equal to 1/2 times the diameter of A plus the diameter of A, all squared. And of course, that's considering if I have an A colliding with another A, and they have this minimum separation, D, okay, where then this is given by dA, and that's also, the diameter of A, not the differential of A, and the diameter of A. And if you also recall, we derived from that lecture on mean free path and collisions, Z, my collision frequency, equals sigma times c bar relative, the relative velocity between the encounter pair, times the number density of molecules in prime of A. And so that's number density, which recall would be N over V equals P over KBT. And of course, that would give us molecules per cubic meter. Okay? So that's our collisional frequency. And recall that our relative velocity is 8 k Boltzmann t divided by pi times mu, all square root, where recall mu is our reduced mass. Okay, So mu equals ma times mb over ma plus mb. And this is, of course, for collisions between a and b, if a and b were different. But if a and b are the same, so if it's the situation where a collides with a, then mu just equals 1/2 the mass times a. Okay? So I'm going to free up some space here. So let's see, we'll get rid of all this stuff and we'll keep, we'll just get a fresh space here. So, okay, for a plus a to go to products, we can now write the collisional density. So in other words, the number of collisions that are happening per unit volume as capital Z, and I'm going to write that as capital Z AA. And that's going to equal 1/2 times little z, that's the collisional frequency, times the number density. It's 1/2 so that you don't double count because it's A and A. And that, if I plug in the expression that we got for little z, that's 1/2 times sigma, collisional cross-section, times the relative velocity between the two pair, times the number density squared. Okay? Because remember, within z there was also number density. And then for a plus b to make products, that goes as capital ZAB, which is going to equal, we'll just write this expression. We don't need the 1/2 because we don't have to worry about double counting. So it'll be sigma times C bar relative times the number density in A times the number density in B. And if you think about these two expressions here, if we think about the units, so this collisional cross-section will be meters squared per molecule. The relative velocity will be meter per second. And the two number densities, because it's number density squared, that's going to be molecule squared divided by meters to the 6th power. Okay, and then the molecule squared cancels with the molecule, and the meter squared times meter gives me meter cubed. So that cancels with meter to the 6th power to give me meter cubed, and per second. So all of that gives me molecules per meter cubed per second. And so then if you think about this, our collisional density has the same units as reaction rate. So for example, we could have wrote that as mole per liter per second. So that's the same as our rate. Okay, so that's nice that that works out. And so now if we expand those expressions, we can now write the absolute collisional density, which is the same as the reaction rate, as sigma, and I'll put in the full numbers here, 8 kBt over mu times pi, all to the 1/2. And now that's going for AB. That's still going to be Avogadro's number squared if we want to turn this into our mole per liter per second. So our Avogadro's number converts our per molecule units to per mole units. And then, of course, our concentrations are given in molarity, and this would give us mole per liter per second, assuming that we've used the right conversion for meter cubed to liter. And then similarly, our ZAA would be given as sigma, and this is going to work out. I'll distribute the 1/2 through because that also ends up being a square. So that's 4 kBt all over pi times m. So recall I had a 1/2 here, and I also have a 1/2 in my mass for A. So that's where this becomes from 8 to 4 all square root. check that algebra if you need to. Pause the video if you have to work out the algebra. And then that's all still Avogadro's number squared, but now that's all times A squared. Okay. So we have a way of writing down the rate with first principles, but more importantly, we have a way of noting what our rate constant is. And if you think about this, all of this is roughly equal to K, our rate constant. And the reason why I say it's roughly equal to K is because in our collisional frequency, we're assuming that every collision leads to a successful reaction. But this won't be the case. As it turns out, we have to consider what the size of the molecules are. We also have to consider how much kinetic energy we have available in our collision. And so if we want to refine these expressions a little bit better, we can now write sigma as a function of what I'll call eta, where eta is going to be defined as relative kinetic energy between the two pairs, which goes as 1/2 mu times c bar relative squared. So again, if this was just the absolute kinetic energy, it'd be 1/2 mv squared, right? But this is now my relative kinetic energy, And now what I really need to do is write my cross-section, my collisional cross-section, as a function of the relative kinetic energy. And to do that, we need to consider the Boltzmann distribution integrated from 0 to infinity, fraction of molecules with kinetic energy eta. Okay, so I'm not going to go into these full details, and I'm going to just present to you the derivation directly, but we're also really considering all values. I've put this from 0 to infinity, but what we really want to consider is values that span from E equaling EA as our minimum. In other words, this EA represents our activation energy. So from the minimum activation energy all the way to cases in which eta is, let's say, much, much greater than our activation energy. So we're going to analyze it through those cases. Okay? So I'm going to erase and start fresh here. Okay, so if we apply that integration, I'm just going to write down the result directly. And we note that our K is coming from, and I'm going to pull out some of the constants, Avogadro's number, for example, and integrating this thing over our limits that we imposed. Okay. Where we're really interested in this as it tends from the activation energy to some value that's much, much greater than the activation energy. What you arrive at for one, just in that limit, when I look at this, from E equals EA all the way to E is much, much greater than EA, we get this expression for the cross-section, which goes as 1 minus EA over E all times sigma, where now this sigma is the physical cross-section, so the size of the molecule themselves. And now what we arrive at this, so in the limit of when EA is equal to E, we notice our kinetic energy cross-section will tend to 0. And as we increase E, right, as we increase this number, our reactive cross-section, or our cross-section as a function of relative kinetic energy, will steadily increase up to some limit of the physical cross-section. So, but it won't get bigger than the physical cross-section when we impose this limit, okay? And when we apply this integral, when we go through and solve it, we come up with the following expression: K equals sigma, the physical cross-section, okay, times 8 kBt, all divided by mu pi to the 1/2 times Avogadro's number times the exponential of negative EA divided by kBt. And this is pretty cool because now what we see here is we have a first principle equation to calculate K directly. And all we need knowledge of is the physical cross-section of the molecule and its activation energy. However, what if we have a large molecule and the molecule has some kind of sweet spot, right? So we call this sterics. And the idea goes as such. So imagine this is our full physical cross-section. This is the actual physical size of the molecule. I'll draw this as some flat world cross-section, let's say. Okay, so I'll call this sigma. And I'll write that as physical cross-section. All right? Well, as a reactant approaches this thing, for collision, we might find that there's only some sweet spot, let's say. Okay? I'm going to define this as sigma star, which is really my reactive cross-section. That's the sweet spot. And for example, a molecule would have to collide with that spot directly to lead to reaction. Otherwise, if it misses that spot, we might have some deflected reactant that doesn't go on to reaction. And so with this picture in mind, we can actually define sigma star with a very simple term, and that's just P times sigma, where this P is my steric factor, and it's really just a scalar. It's really just, it's a number that's less than 1, and it's really just defining this thing in this geometric sense. Okay, so with that in mind, we can rewrite our expression for K, and I'll rewrite that here. So that's going to be now P times sigma times 8 kBt all over pi mu to the 1/2 times Avogadro's number times the exponential. Let me rewrite that. So that's NA times E raised to the negative EA over RT or kBt, depending on what units you have EA in. And then actually what you hopefully recognize this as, this pre-exponential term is A, which we derived last time, and that is our frequency factor. And which, recall, in the limit of EA approaching 0, our rate constant just approaches that of the frequency factor. In other words, the rate constant only depends on the frequency of collisions. Okay? And so oftentimes, let me just free up some space here, it could be really difficult to actually calculate our actual frequency factor, P times sigma times 8 kBt over pi mu 1/2 times NA. And I'll define everything that's multiplied by P right here as A prime, which is really the theoretical value of A. Because this steric factor, that's a really difficult number to actually calculate from first principles. You typically have to do a comparison of experiment and theory to actually give the steric factor. In other words, A will equal P times A prime. And so recall, we can calculate A prime, but if we go on and do our experiment at several different temperatures, right? So recall now, we know that K equals A, e to the negative EA over RT. And if we take the natural log of K, We know that we're going to get negative EA over RT plus natural log of A. Okay, so if we did several experiments at different temperatures, right, and analyze the data as natural log of K versus 1 over T, we might see something that looks like this. And we fit a line through it, and we can estimate what the experimental value is, experimental. And then if we calculate what this theoretical value is, then we could actually then determine what our frequency factor was if we really wanted that first principles analysis. Okay, that concludes the lecture on collision theory as it pertains to chemical kinetics.